In classical physics, if we knew the position and speed of suns and the planet at one time, then we could use Newton's laws to calculate the state of solar system at any other time, whether in future or in present or in past. But this is not the case with the physics which deals with subatomic particles. Today in this video we are going to discuss about a principle which will explain us why this case cannot be applied in quantum physics or in the physics of lower subatomic particles. So without wasting our time, let's start this video. To understand this principle more efficiently, let's first understand what was there in physics before the introduction of this principle. Lord Rayleigh and Sir James Jeans suggested that a hot body or a body such as a star must radiate energy at an infinite rate. According to the law, we believed at that time a hot body ought to give an electromagnetic wave, such as radio waves, visible light, or X-rays, equally at all frequencies. For example, a hot body should radiate the same amount of energy in waves with frequency between 1 and 1 million waves a second, or in a wave with frequency 2 and 3 million waves a second. Now, since the number of waves a second is unlimited, this would mean that the total energy radiated would be infinite. In order to avoid this obviously ridiculous result, the German scientist Max Planck suggested in 1900 that light, X-ray and other waves could not emit at an arbitrary rate, but only in certain brackets that he called quanta. Moreover, each quantum has a certain amount of energy that increases with the increase in frequency of the wave. So at a high enough frequency, the emission of single quantum would require more energy than was available. Thus the radiation at higher frequency would be reduced, and so the rate at which the body lost energy would be finite. The quantum hypothesis explained the observed rate of emission of radiation from hot bodies very well, but its implications for determinism were not realized until 1926, when another German scientist, Heisenberg, formulated his famous uncertainty principle. In order to predict the future position and velocity of a particle, one has to be able to measure its present position and velocity accurately. The obvious way to do this is to shine light on the particles. Some of the waves of the light will scatter by the particles, and this will indicate its position. However, one will not be able to determine the position of the particle more accurately than the distance between the wave crest of light. So one need to use the light of a short wavelength in order to measure the position of the particle precisely. Now, by the Planck's quantum hypothesis, one cannot use an arbitrary small amount of light. One has to use at least one quantum. This quantum will disturb the particle and change its velocity in a way that cannot be predicted. Moreover, the more accurately one measures its position, the shorter the wavelength of the light that one needs, and hence the higher the energy of a single quantum. So, the velocity of the particle will be disturbed by a large amount. In other words, the more accurately you try to measure the position of the particle, the less accurate you can measure its speed, and vice versa. Heisenberg showed that the uncertainty in the position of the particle times the uncertainty in its velocity times the mass of the particle can never be smaller than a certain quantity, which is known as Planck's constant. Moreover, this limit does not depend on the way in which one tries to measure the position or velocity of the particle, or on the type of particle. Heisenberg's uncertainty principle is the fundamental inescapable property of the world. The mathematical formula of Heisenberg's uncertainty principle is delta P into delta X is more than equal to Planck's constant by 4 pi. Delta X is uncertainty in position, delta P is uncertainty in momentum, H is the Planck's constant. The uncertainty principle have profound implication for the way in which we view the world. Even after more than 50 years, they have not been fully appreciated by many philosophers and are still the subject of much controversies.